Thunderstorms are some of the most violent and most focused forms of severe weather on Earth. And we're looking here at the three different types of thunderstorms that we're really going to study this semester. Animating in the upper left, we have a squall line, and we'll reference this as a mesoscale convective system throughout the class. Long lines of thunderstorms like these can often produce a lot of damaging winds. In the bottom, I have a picture of what we'll call an ordinary thunderstorm. So this is one that tends to form in a lower wind shear environment and tends to not produce much severe weather. But kind of the big dog in the room here would be this one. It's called the supercell. Even though I call it big, it's not nearly as large of a storm as the mesoscale convective system, but pound for pound, this is likely the most powerful expression of weather on Earth. It can produce incredibly large and powerful tornadoes, huge hail, and straight line wind damage that is just incredible. So we're going here. This is what we're about to study. But let's just step back and start off by learning about the ingredients that are necessary to make these massive thunderstorms. Because ultimately, if you ever want to observe one safely, or if you ever want to try your hand at storm chasing, you need to know these four crucial ingredients. So a bit of a background on thunderstorms. First of all, we call the cloud type that makes them the cumulonimbus cloud. This is a cloud that develops vertically, and you'll see a lot of videos of these types of clouds in this lecture. And of course, the thunderstorm must contain lightning and thunder. Now, thunderstorm season in the United States typically begins in March and ends in September. And I got a graph down here on the bottom right that kind of shows us day by day. This was just data from 2006, just as an example of when we had severe weather reports. So that either being from hail, wind, or tornadoes. Now you can see that most of the activity is right in there, March to September, but that does not mean we can't have severe weather outside of that or any thunderstorm activity outside of that window. Looking at the whole of the United States, really our greatest concentration of thunderstorm activity will be along the Gulf Coast in Florida. Basically, we can have year-round thunderstorms down here. There's also another smaller pocket here that's right along the front range of the Rocky Mountains. Due to some strong dynamical heating plus some favorable winds, we can get storms to blow up and roll off the mountains quite frequently. So when you just look at this map, it's the number of days per year with thunderstorm activity. Now, when we start to think about the problems versus the benefits, let's start off with the problems first. The human life loss, on average, the 10-year average is 223 deaths per year. Now, that's deaths coming from flooding, that's from hail, that's from winds and tornadoes and lightning. So that's a lot of fatalities per year, and an argument can be made that most of those fatalities are preventable. When it comes to property damage, we estimate somewhere around $12.5 billion spent cleaning up after these storms, with an additional $2.4 billion spent on agricultural damage, most of this coming from wind and hail. But I want to make sure that we understand that without thunderstorms, without the regular interaction of our thunderstorms across the breadbasket, this is the Corn Belt, the middle part of our country, we would not be able to produce the large amount of food that we can in the United States. And that's because each one of these thunderstorms, even these little ones you see popping up in the back of this picture that I took here over this cornfield, even these little ones here can contain billions of gallons of water. And we need that regular rainfall interaction in order to make these crops grow. So it's kind of a balance. It's the good with the bad. And it's kind of if we want to call it a necessary evil, to have these massive and powerful thunderstorms move across the United States to bring the life-giving rain we have to the middle part of our country. So this is our overview. What I want to get really going with is this video. It's one of my favorites. It's a compilation of time-lapse video of massive thunderstorms kind of boiling and erupting into the atmosphere. And when you're looking at this, this is really the thing we want to try to understand about our atmosphere. Why? In the troposphere, that's the layer we live in, why is the atmosphere able to bubble like this? Why does air rapidly rise, fighting gravity, producing these massive thunderstorms? Because the amount of energy released in these thunderstorms is absolutely staggering when you think about it. It dwarfs what we have in our nuclear weapons. It's incredible to see this happening. So we need to study how and why this occurs. And what I want to say is this. If you understand what's going on in this video, you can get why our atmosphere is able to do that. This is one of my favorite videos. I'm going to take you to Reno, Nevada here, and you're watching a hot air balloon race. This was back in 2006. And you can see each of the balloons being filled here with hot air, and they become buoyant. We fill that canvas with hot air. It becomes less dense than its surroundings, and it takes off. Now here's the connection I want you to make. I think it's easy for you to see and kind of grasp here that inside of that canvas there is the hot air, and it's being held in there by the balloon itself. But what I want you to focus on and stress on in this is that the atmosphere has the ability to make these little pockets of air that kind of move about all by themselves, staying contained to themselves as they move through the atmosphere. And ultimately, their vertical motion is a response of their buoyancy, which again is a difference in the density of the medium. So we have hot air on the inside, less dense, cold air on the outside, more dense. That is the theme, really the big theme of this lecture. So let's try to understand this. In atmospheric sciences, we often discuss the stability of the atmosphere. The stability is defined as the resistance to change. You got a couple of simple examples up here. You got a boulder in the middle of a valley here. You try to push that up the valley here. If you let go, you remove the force of your arms pushing it up, it will return to its initial position. So things that are stable go right back to where they started. An unstable situation would be like this. You have the boulder on top of the hill. A small force will cause it to accelerate away from its initial position, like you see over here. You see, ultimately that's our goal. How do we get air to accelerate upward from its initial position without any help? That's what we want to see. So we're going to define something in this class called a parcel, an air parcel. It says down here that an air parcel is just a blob of air that we're going to identify as it moves throughout the atmosphere. We're always going to be comparing what happens inside of the air parcel to what happens outside of the air parcel. We're going to call what happens outside of the air parcel the environment, okay? So when you see this picture of this thunderstorm, you can consider the clouds the parcel. Maybe a whole bunch of parcels, maybe one big parcel, I don't care. Think of it any way you want, but it's the parcel we're discussing. We're going to be comparing the internal temperature to this system to what's on the outside, which is the clear blue sky. And just like the hot air balloon, if I can get the air inside of the parcel to be warmer than the air on the outside, it will ascend. Now, how does that happen? Well, it turns out in the atmosphere, chunks of air, as they move about through the atmosphere, tend to behave according to what we call an adiabatic process. And if you've never heard that term before, here's the easy way to think about it with relationship to atmospheric sciences. Basically, it means no mixing of the air inside of the chunk of air with the air outside. So basically, what happens inside the parcel stays in the parcel. And that is how these parcels of air kind of survive without mixing out with the environment that's around them. Here's our key idea through the first half of this lecture. We're going to be comparing the temperature inside the parcel to the air temperature outside of the parcel. If the air temperature inside the parcel exceeds or is greater than the air temperature outside, the air parcel will ascend. Keep that in the back of your mind through the first half of this lecture. So let's dig into this here. First, a couple of simple definitions. Rising air cools by expansion. As air ascends, this parcel of air, as it rises, the atmosphere pushing in around it basically pushes less and less and less hard as it ascends. Why? Atmospheric pressure, as we learned a long time ago, decreases with height. That allows the parcel to get bigger and bigger and bigger, and it basically imparts some of its energy by expanding against the environment that it's floating into. Therefore, it cools as it rises. This is the same way by which, an aerosol can that maybe has hairspray in it or compressed air cools as you squeeze the trigger as the air comes out. Now, by the same token, when you allow air to descend in the atmosphere or sink in the atmosphere, it warms by compression. If you've ever held a bicycle pump and pumped it up, you know that the cylinder, as you hold it, as you're pumping the air in there, it gets hot. So that's the idea that we want to start off with here. But here's the cool thing about atmospheric sciences and about physics. Basically, the rate of cooling or the rate of warming is discoverable. In other words, we can write equations to help us understand it. And one of those equations is called the first law of thermodynamics. Solving it gives us this number. It's called the dry adiabatic lapse rate. Now, the dry adiabatic lapse rate, the name tells you what it is. Dry. That means the relative humidity inside the parcel is below 100%. Adiabatic, no mixing. And a lapse rate is just a change in temperature, so degrees Celsius, over a change in height, kilometers. The dry adiabatic lapse rate, as discovered by solving the first law of thermodynamics, means that a parcel of air, as it ascends, cools 10 degrees in temperature for every 1 kilometer that it goes up. By the same token, if you take that same dry chunk of air and have it come down in the atmosphere, it will compressionally warm at that rate, meaning that it warms 10 degrees Celsius per 1 kilometer as it descends. Now what's really neat is this. There's a second rate I want you to learn. It's called the moist adiabatic lapse rate, and its value is approximately 6 degrees Celsius per kilometer. Now what you notice is that's a slower cooling rate than the dry rate, and the only change is the word moist. So the notes here say a parcel of air with a relative humidity of 100% cools at this rate as it ascends. Now what that means is as the parcel is rising and attempting to cool, something's happening inside of it that doesn't let it cool at 10 degrees Celsius per kilometer, but slows the cooling down to 6 degrees Celsius per kilometer. And what is happening is that we're actively making clouds. Condensation is a warming process. So basically we're pumping in about 4 additional degrees of heat into this, stopping the cooling from cooling at 10 and getting it to cool only at 6. And here you are seeing that whole process active in a time-lapse video. It's one of my favorites. It's called explosive convection. We are seeing air rapidly ascend, maybe 50, 60, 70 miles an hour going straight up, and it's releasing vast amount of heat. Well, the parcel is the cloud. The clear sky around it is the environment. And to fully understand these principles here of cooling and expanding air, warming and compressing air, and to understand these lapse rates, let's take a look at this situation down here. So I'm going to launch 2 weather balloons. One weather balloon is going to go straight into this cloud, and we'll consider that balloon going into the parcel. We're going to launch another weather balloon outside of the cloud. In fact, let's launch this one first. So as this balloon ascends, we're going to trace out its temperature and dew point temperature profile on this sounding diagram. Check it out. As the balloon ascends, there you can see the rate of temperature change. That's the far right line. Then you can see the rate of the dew point temperature line. That's the far left line. So what we're seeing here is as this balloon ascended, it measured the temperature, that's this line, and the dew point temperature, which is this line. It measured that profile of the atmosphere. Now watch this. I'm going to launch another balloon that's going to stay in the parcel as it ascends. Here it goes. As the balloon ascends, it measures a much smoother transition of temperature and dew point. And that's because inside of this parcel, this thunderstorm, the temperature is going to cool either at 10 degrees Celsius per kilometer, which is this branch of the line down here, or 6 degrees Celsius per kilometer, which is the slope of this line here. This is basically below the cloud, and this is in the cloud. Now what we want to do is we want to play that comparison game. Let's compare the temperature of the cloud, the parcel, with its environment to see if it is warmer than its surroundings. So here those lines are again. Outside of the storm, we see this. Air ascends, its temperature line here, dew point temperature line here. We're going to call that the environment. Let's put it down here in our bottom graph so we can see it a little bit larger. Inside of the storm, or inside of the parcel, we see this temperature change. Below the cloud, 10 degrees Celsius per kilometer. In the cloud, 6. Let's put that line on this one as well. Now, the notes over here on the right tell us exactly what we're going to do here. I'll read it to you. Since we know exactly how an air parcel's temperature will change, if it's lifted into the atmosphere, that means it's going to cool at either 10 degrees Celsius per kilometer or 6 degrees Celsius per kilometer, cools at 10 below the cloud and 6 in the cloud, we can plot a hypothetical parcel line on any sounding to tell us if that environment is capable of producing a thunderstorm. So this is kind of a what-if situation that we play all the time. Here is what I want you to remember. You can see that this sounding diagram has temperatures warming as you go to the right, and we're ascending in the atmosphere. That's the y-axis. Here's the game we're going to play. At any level, if the parcel is warmer than the environment, the atmosphere is unstable. If the parcel is cooler than the environment, it's stable. You will get thunderstorms in unstable atmospheres, and you won't get them in stable atmospheres. So this is our main goal as we continue to work our way through these stability notes. Every parcel line is going to have a shape something like this, okay? And it's a really interesting shape I want you just to get familiar with. It has basically one distinct shift in it, and that happens right here. And what I want you to remember is that that distinct shift happens at the base of the thunderstorm. Below it, the parcel cools at a rate of 10 degrees Celsius per kilometer. That's the dry adiabatic lapse rate. Above it, it cools at the moist adiabatic lapse rate, which is approximately 6 degrees Celsius per kilometer. What this means is, if our cloud looks something like this, and that's what my clouds look like in Microsoft PowerPoint, the base of the cloud happens right here. And I'll tell you in a moment why the top of the cloud is right up here. So this distinct mark right here, where it shifts from this slope to this slope, happens at cloud base. And we're going to give that a new name in just a few moments. We're going to call that the lifting condensation level. We'll come back to that in just a second. So check out this awesome video here. Let me fast forward a little bit. This is a massive supercell thunderstorm. Why do all of these huge thunderstorms have flat bottoms, a big bubbly spot in the middle here, and then flat tops? We want to answer those questions. Why do they have these three very definable characteristics? Flat tops, flat bottoms, and this middle part that just looks like it's boiling. Let's try to understand that. To do that, I want to learn about three distinct points inside the storm. So here's a huge thunderstorm we're seeing off in the distance. Why does the cloud base have this nice flat edge to it? Well, we call cloud base the lifting condensation level, or the LCL. As it says in the notes, it's the point above the ground that we got to lift the air to get condensation to begin. So we know that as air rises, it cools, and as it cools, the air's relative humidity increases. And we need to find that point at where the temperature equals the dew point temperature and the relative humidity is 100%. So watch the animation here. The air is going to rise, and all of a sudden it hits this spot right here. Again, we call this the LCL, or the cloud base. To see this in real-time video, check this out. Here's air rising. It's behind the trees, but it's rising, and it reaches its saturation point right there as it goes in to make this cloud. This is actually a very special type of cloud called a wall cloud, something I'll be teaching about very, very soon. But can you see the air rising, reaching a relative humidity of 100%, and the cloud forming? That's the big idea. Look at it right here. See that? Air rapidly ascending, cooling as it expands, reaching its relative humidity 100%, making the cloud. Why is this flat? That's our thing we're trying to figure out here. Well, that's at the bottom. Let's step it up and try to find the next level. At some point above the cloud base, typically, there's something called the LFC. It's the level of free convection. Did you remember in the video we watched a few moments ago about the hot air balloons ascending, that they filled those hot air balloons full of hot air, but at one point, all of a sudden the balloon had enough hot air in it that became buoyant, it just took straight off and went up? That's basically this point inside the storm. It's the level to which you got to get the air to reach for it to just take off freely, all by itself, and go straight up in the atmosphere, outdoing gravity by these buoyant forces, again, just due to heating. So it's a point above the ground that the parcel first becomes warmer than its environment. And that's the key phrase, first becomes warmer than its environment. Above that point, the parcel can rise on its own because it's buoyant, like the hot air balloon. And this is the part that marks the middle part of the storm, where it's really, really bubbly, where it makes all of that really violently rising air. Okay? From the LFC, level of free convection, all the way to the top of the storm, this is the part of the storm that is unstable. It's the part that is unstable. In that part, air rapidly ascends all by itself, and that is what we're trying to figure out and understand. Okay, at the top of the storm, we slam into the very, very stable stratosphere. The stratosphere is marked by a huge inversion. Temperatures are increasing there. And when it happens, that air hits the updraft hits that stable layer and then spreads out horizontally. We get what's called an anvil cloud. But in atmospheric sciences, we call this point the equilibrium level, the EL. It's when the parcel hits the stable, very warm stratosphere and spreads out horizontally and marks the top of the storm. All right, those are our 3 points. One cool picture I want to show you here. This was taken from the International Space Station. Here we are looking down on top of a thunderstorm. This is where the storm hit the equilibrium level. This is the anvil cloud. But this storm actually had so much momentum in its updraft, it briefly penetrated into the stratosphere. We're seeing what are called overshooting tops. Pretty amazing picture to see here from the space station. Now, to watch this all again, let's start this video right about here and see this all unfold again. There it is, massive supercell. Look, flat base, that's our LCL. The bubbly part in the middle starts above the level of free convection. Here it is again, kind of zoomed in. Beautiful to see that rising air. Slams into the stratosphere and hits the equilibrium level. This is what we're trying to understand. Why and how does the storm do that? So this is the technical part. So check this out. I've got a sounding here. I've got 3 lines. Let's label them. Here's my environmental temperature line, the thick black line on the right. Here's my environmental dew point temperature line, the thick black line on the left. And this thin line right here is my parcel line. Now remember what I taught you about that parcel line. It has a very distinct shape. So let's start off first by identifying the level of free convection, the LFC. The level of free convection marks the first point where the air parcel becomes warmer than its environment. Now, how do you find this? Start from the bottom, follow the air parcel line, and look for the first time that it crosses the parcel line, which in this case is happening right here. Read off that pressure, it's at 800 millibars. Look, beyond that point, the farthest to the right line is the parcel line, meaning it's the warmest. Okay, not bad. This marks the bubbly part of the storm, the unstable part of the storm. The top of the storm is marked by the equilibrium level. That point is happening right here. That's where the parcel line again crosses the temperature line, and at that point the parcel becomes cooler than its environment again. So that marks the top of the storm. Cloud base, remember how we find that? We look for that kink in the line. Notice how it's cooling at 10 degrees Celsius here and 6 degrees Celsius there. So that very subtle but noticeable kink in this case is happening at 900 millibars. Now, when we're looking at soundings like this, picking out these lines in these locations can be difficult at first. So I want to teach you of an indice. In fact, we're going to learn about two different indices. You know, we like to monitor the stock market and its performance by looking at indices. We're going to do that here with two. First one's called the lifted index, abbreviated LI. It's found by going to the point in the atmosphere where we have 500 millibars right here and reading off the temperature of the environment, which is this point where it crosses this black line, and subtracting from that the temperature of the parcel, which is here. In this case, the temperature of the environment, if I just read straight down on the graph, is minus 26 degrees. The temperature of the parcel, if I read straight down on the graph, is about minus 23, crosses right about here. Minus 26 minus negative 23 is negative 3. That means the parcel is 3 degrees warmer than its environment at 500 millibars. And just like with a hot air balloon, just like with what we've been explaining, if it is warmer than its environment, it is buoyant and it will ascend. Therefore, at that point, because this is negative, the atmosphere is unstable. Now, when these diagrams were designed, area on these diagrams is an expression of energy. So what I want you to see next is I'm going to shade in something called CAPE. CAPE stands for Convective Available Potential Energy. It can be shaded on these diagrams for any point where the parcel is warmer than its environmental temperature. You see from here, from the LFC, all the way to the equilibrium level. In a nutshell, the more of this area there is, the more powerful the updraft and the more powerful the storm. In this particular case, this storm looked just like this. It's flat bottom here at the LCL, the lifting condensation level. It's unstable part beginning right here at the LFC, and the top where the anvil is located right there at the equilibrium level. Now, I realize that's the first time a lot of you have seen this, and it's kind of complicated to look at, but let's get some practice with it, okay? I got two soundings. Now, these are real-life soundings, one from Lincoln, Illinois, back on November 17, 2008, and again, another one from Lincoln, Illinois, on August 5th, 2008. Now, check this out. On each one, I have a parcel line. Let's look at the lifted index and the CAPE values for this one. Let's start on the left side diagram. Remember, lifted index is the environmental temperature minus the parcel temperature. Go to 500, that's right here. There's my environmental temperature. There's my parcel temperature. Go straight down to read off their values. And what I get here is the temperature of the environment, minus 24 degrees Celsius. The temperature of the parcel, minus 43 degrees Celsius. Negative 24 minus 43, negative 43 is 19. That means the temperature of the environment is 19 degrees warmer than the parcel. That means there's no way that an air parcel will ever ascend up to that point, which means this is going to look like a crystal clear, beautiful fall day. Not much really that I ever want to chase. I never made a career out of chasing crisp fall days. But what I like to have happen is stuff like this. I will never forget this day. Let's do the math first. Parcel temperature, environmental temperature, where they crisscross 500 millibars, read them off. Environment first. Right down here, negative 9, negative 8, something in that range. Right over here, -5, not -5. The difference between the two, -8 minus 5 is 13. Now look at the chart. The chart says if our lifted index values get below minus 6, we are extremely unstable, severe storms probable, tornadoes are possible. This is an incredibly unstable situation. Look at that, minus 13. That means the parcel's 13 degrees warmer than its environment at 500 millibars. Check out the CAPE too. Now, a lot of research has been done to understand CAPE values with respect to, the potential for tornadoes. Generally, the most violent tornadoes form with CAPE values of at least 1,000 to 1,500 joules per kilogram. Now, don't worry about that unit for our class, okay? But 1,500 joules per kilogram will make you a pretty massive and powerful storm. On this day, we had 7,000 joules per kilogram of CAPE. Oh, and by the way, there is no CAPE over here because the parcel never once becomes warmer than its environment. But I want to show you what happened on this day. Check it out. Upper left-hand corner, radar animation of a huge cluster of thunderstorms moving through Chicago. On this day, 5 separate tornadoes formed inside these storms. Look at what happened when the updraft, the rising air in the unstable part of the storm, slammed into the stratosphere, the equilibrium level. See the huge anvil cloud that it formed? And check this out. There was a Cubs-Astros game that night. Thankfully, a tornado did not hit Wrigley Field, but it did produce these strong, sustained winds of 70 miles an hour. So pretty incredible event here. So this just goes to show you the value of forecasting the really, really unstable air, because it can do stuff like you see here. Pretty rough night for the Chicagoland area. All right, here's another example. Now, in atmospheric sciences, once you get a little more into our more advanced classes, we look at a little bit different sounding diagrams than what I've been teaching about. This is called a skew T diagram, but you can read it the same way. Parcel line goes right there. Right in through here is the unstable part of the storm. We had a lifted index of minus 8.55 and CAPE values 3,135 joules per kilogram. So that's a lot of CAPE. On that day, this happened. Here we are in Moore, Oklahoma, May 20th, 2013. Powerful EF5 ranked tornado going through town. Look at that sucker. Now, what's amazing is because of a sounding diagram like this, storm chasers and meteorologists all over the country knew this was coming. It was there. It was forecast very, very well. And this massive, powerful tornado, well, we had warnings out for it far in advance by the time it got into Moore, Oklahoma. Now, it did an enormous amount of destruction, but so many lives were spared because of our understanding of the destabilization of the atmosphere. So very, very important thing to learn here. Now, just to help you get a little bit more practice, I want you to check out the diagram on the right, showing you the sounding line first. So look at it. It has that very distinct shape, the kink being right here. Okay, so you see that? Here's the temperature of the environment on this day. Now, let's answer some questions. What is the pressure at the LCL, the lifting condensation level? Remember, that's cloud base. Your goal, find the kink in the parcel line. And again, it happened right there. If we read over, that's 900 millibars. So in this case, B is the correct answer, 900 millibars. Let's try another one here. What's the pressure level at the LFC? That's the level of free convection. You're reminded to go, okay, this is the point where we're looking for the parcel first becoming warmer than its environment. And if I look from the bottom here, look for the point where the blue line first crisscrosses the black one on the right and it happens right here. That is at 750 millibars. So the answer to this one is D. Our next question. What is the pressure at the equilibrium level? Well, we go to the top of the sounding for that, looking for where the blue line, the parcel line, again crosses the temperature line. And it's happening way up here at 175 millibars. All right, how about this question? What is the value of the lifted index? Well, if I come over here to 500 millibars, my temperature line crosses right there. So if I go down and read this off down here, we could probably call that, I don't know, -7. And over here we see that the parcel line is about -12. Well, -7 minus -12 is -5. And this is most certainly capable of producing severe thunderstorms simply due to this big unstable pocket right in through here. How about some quick eye clicker question reviews like we would have done in class? All right, check it out. True or false? The atmosphere is said to be unstable if a parcel's temperature is warmer than its surrounding environment. That is absolutely true. Here's another one. True or false? A negative lifted index indicates an unstable atmosphere. That is also true. Remember, negative lifted index, thunderstorms. Positive, no thunderstorms. How about this one? The stratosphere is defined by a large temperature inversion. So the stratosphere is defined by a large temperature inversion. Is the stratosphere a stable or unstable layer in the atmosphere? Well, we want the temperature to get cooler and cooler and cooler with height so that our parcels can be warmer than their environments. So if the stratosphere is a place where it's getting warmer with height, that is a stable layer. And by the way, that's why we like to fly our commercial aircraft there. It's stable. It doesn't bounce around very much. Stable. That's a stable layer. Another one here. Which body of water is the primary moisture source for thunderstorms in the Midwest? So this is interesting. We're going to make a quick shift here and talk about another ingredient. Well, the primary source of moisture for those thunderstorms that come over us here at the U of I campus, it's not the Pacific. That moisture is blocked mostly by the Rocky Mountains. It's not the Atlantic either, because in order to get moisture from the Atlantic, we gotta have a strong east wind. It's not the Great Lakes. While they're huge lakes, they're not large enough to really modify the weather for the entire Midwest. Our answer is the Gulf of Mexico. The Gulf of Mexico, there's a almost free and clear path for moisture to be transported from the south, and we get south winds all the time, right into the Midwest. By the way, the Muhammad Aquifer is the stratified rock layer that's below us all right now in Champaign, and underneath that, there's incredible amounts of very, very, very good water. So remember, it's the Gulf of Mexico that supplies us with most of our moisture for our thunderstorms. All right. When we start talking here about these other ingredients, the other ingredients are going to go a little bit faster. You see, the tricky one to understand is the instability of the atmosphere. The second ingredient here is called a trigger mechanism. It's just anything that can cause the air to rise. That can be what we call surface convergence. Air just coming together at the surface and rising. It could be fronts. This is where density differences from cold and warm air or hot and dry air versus hot and humid air, where they collide to make air rise. You can have what's called orographic lift. That's where we get air to go over mountains. You could also have a sea breeze, which is where we have basically air masses colliding over like the Florida Peninsula. We'll take a look at that in a few seconds. Or you can simply have just rising thermals of air. We're going to look at all of these kind of in sequence here. Let's talk about the front first. Here we can see a cross-sectional diagram of a cold front. So here comes the really, really cold air, maybe from Canada, racing toward the south. Because the cold air is much more dense than the warm, moist air out ahead of it, the warm, moist air just rises right over the top of it. When air rises, it expands. Expanding the air leads to condensation. Condensation releases heat and it makes clouds. And if the atmosphere above that front is unstable, boy, it just rapidly rises to make these huge cumulonimbus clouds, CB, like you see right there. So a front is just forcing air to rise. Let me give you a good example of this. This is a satellite image taken over at Nebraska and Kansas. And I'm going to show you two different big air masses that were in play here. We had one coming out of the desert southwest, coming off in this direction, and another one coming out of the southeast, which is coming from the Gulf of Mexico. I've kind of color-coded these according to their temperature and moisture characteristics. This one was hot and dry. This one was hot and humid. And where these two air masses collided, right here where I'm tracing, there was what we call a dry line. And on this day, look at how the thunderstorms erupted. 53 separate supercell thunderstorms, many of which producing tornadoes. It's incredible to see how those two air masses collided to get the air to rise. Let me give you another example here. Here we can see on satellite air colliding at the surface. This is a surface convergence. This is a front causing the air to rise to make these massive thunderstorms. What's going on in this case is this. I got air on one side coming from the north and northwest, on the other side coming from the southeast. And when that air hits, it rises. And rising air causes the air to expand, cool, you get condensation, and clouds forming just like that. So those are the storms that we see forming right here just simply due to the converging of air at the surface. It's got one place to go, and that is up. Now, let's take a look at the orographic lift. You force air to go over the top of a mountain, it will rise, expand, and cool. And that's why we get clouds over mountains. Check this one out down here. Here we can actually see the LCL very clearly. See that flat cloud base? The air is rising from this direction, going right over the top of the mountains, and it's clearly getting into some unstable air, which is why it is rapidly ascending like you see right here. Now, I'm going to show you something kind of neat here. the air doesn't always have to be unstable when it goes over mountains. Here's a view of Mount Rainier, where some air is going over the top of it that's very stable. We're producing what's called a lenticular cloud. The air is rising, but instead of forming a bubbly layer above this, it's this flat sheet-like cloud. This air is not unstable, but it's still forced to rise by the mountain. The cloud's made on this side, and it evaporates on that side. Maybe a better way to see this would be to look at an image or an animation like this. Check this one out. Here we're seeing what's called the Apostle Mountains, and we're seeing the air coming over the back side of them. Notice that as the air descends, it's compressionally warming. And if you warm the air, you're automatically lowering its relative humidity, making the cloud evaporate. So clouds are a fantastic source for making, mountains are a fantastic source for making clouds. Just a beautiful view of them right here. All right, let's get on to our next one. Here's one of my favorite animations. This is over the southern tip of Florida, and you're watching the sea breeze create these massive thunderstorms. See them right there? These thunderstorms even putting out their own outflow boundaries, which are triggering other thunderstorms. So what you're seeing is just this incredible event where we're triggering thunderstorms by a sea breeze. Now, how does the sea breeze work? Well, it really depends on a boundary between land and water. And so you can see that these storms first formed right on that boundary. Let's try to understand what's going on here. Here's a top-down view, and here's a side view of the Florida Peninsula. Now, in the middle of summer, the Florida Peninsula gets very, very hot, and even though the water that surrounds it is warm, it's still cool compared to the island, or compared to the peninsula. So what ends up happening is throughout the day, we end up developing this pressure gradient that sends wind from the water over to the land. The moment that the winds kind of reach the land, there's a reduction in, there's an increase, I should say, in surface friction. So the water's smooth, the land is more rough. That slows down the movement of the wind, and that forces the air to rise. And as air rises, it expands, cools, and you get condensation. And that condensation makes these huge thunderstorms. So that's why they often form right there on the edge. Now, the last one I'm going to talk about is rising thermals of air. Check out this video over here on the right. You're actually watching a pretty cool video here of a bunch of broad-winged birds, more like hawks, out flying, and none of them are flapping their wings. It's because they're flying on top of rising thermals of air. You see, the atmosphere can kind of heat up certain pockets of air, causing them to rise, and as they ascend, they can eventually cool enough to form clouds and precipitation. It's not doing it over here just yet, but these birds are basically floating on these rising pockets of air. We call them rising thermals. You can also hang glide on these things as well. Again, in each one of these trigger mechanisms, it was about getting the air to rise. All right, our third ingredient is, I think, a little bit easier one to understand. In order to make a thunderstorm, you can't have dry air. You gotta have really, really moist air. You see, the moist air is the ultimate fuel for the storm. Why do we call it that? Well, when we take moist air and force the water vapor to condense, it releases enormous quantities of heat. Now, our primary moisture source is the Gulf of Mexico. Our secondary moisture source is from what we call evapotranspiration. Now, you know that in the Midwest, we grow a lot of crops. An acre of corn on an August day can actually evaporate into the atmosphere 3,000 to 4,000 gallons of water. So we can have supplementary moisture put into the atmosphere in addition to the Gulf of Mexico moisture from our vegetation. It's called evapotranspiration. Now, when I storm chase, I usually don't chase any time where the dew point temperature is less than 60 degrees. So you see this white line I put on our dew point map here? It's kind of showing you where everywhere on the south and east of that line, the dew point is 60. You see the bubble right in here of 75-degree dew points? That is disgusting air. That's incredibly humid air. This bullseye, I should say. This bullseye here is from the additional moisture put in by the drying down of our crops in the middle part of the country in August. Incredible to see that. Huge thunderstorms blew up on this day. You just saw them a few moments ago in Chicago during that Cubs-Astros game. Now, we typically get, again, most of our moisture from the Gulf of Mexico. And what I want to show you here is what happens when all that moisture finally collides to make massive storms like these. You see, I teach you about these ingredients because when they all come together, you can produce these violent expressions of weather, these massive thunderstorms. I'm watching here a bunch of different supercells forming just over the Great Plains. Incredible to see this. So you see, there's a point behind me teaching you all of it. None of this happens without those first three ingredients. Okay, let's take this and talk about the formation of the storm. Thunderstorms tend to go through three stages. The first stage is marked by the development of an updraft. Updrafts are simple. It's where you have warm, moist air that's rising. Remember, something triggered it to rise. A front, a mountain, a rising thermal, a sea breeze. When the air rises, if the atmosphere is unstable, it continues to ascend. We know that it cools, that leads to condensation, and it makes clouds. Now, this rising air can sometimes rise very, very quickly. You never want to fly a plane through a huge cumulus cloud like this. It would be an incredibly rocky and very painful flight. Now, as this air continues to rise, it will eventually hit the tropopause. That's the boundary between the troposphere and the stratosphere, the stable air above. When that air hits that level, we get the anvil cloud. And at this point, the storm begins to make its downdraft. All that moisture that is ascending, well, as it ascends and builds into these cloud droplets, they grow. We start to build these rain droplets, and they have to fall. And they fall, and as they fall, they outdo gravity and produce something called a downdraft. Downdrafts occur as we kind of mix in a little bit of dry air, we kind of cool things down, and the precipitation begins to fall. Now, as it falls, it drags some of that air down with it. And the result is, beneath the cloud, you get what's called a very cold, dense pocket of rapidly descending air full of precip. We call that the downdraft. So it's pretty simple. The updraft goes up, the downdraft comes back down. So what goes up must come back down, and that's ultimately how the thunderstorm ends its life cycle. As it dissipates, the updraft is canceled out by the downdraft. An ordinary thunderstorm is rarely severe because it lacks our fourth and most important ingredient. We're going to come to that ingredient in just a few moments. Updraft, downdraft. Let's take a look at what they look like first, though. Over here on the left-hand side, time lapse of an updraft. You can see the air rapidly ascending. You could see it producing an anvil cloud. You can see the stratosphere above. You can see the unstable layer above the LFC. This is what an updraft looks like. Rapidly ascending air that is cooling because it is expanding, that leads to condensation and clouds. On the flip side, let's get beneath the cloud to watch a downdraft. When the downdraft forms is when all the precipitation comes falling out of the storm. This is a very powerful downdraft. See it right there? That is called a microburst. We're seeing an incredible amount of moisture falling out of the storm all at once, probably at speeds in excess of 100 miles an hour. You see, that's what happens when we have really focused downdrafts. But again, it's what goes up compared to what comes down. Watch that downdraft one last time. It's going to come out right here. There it is. Incredibly powerful descending air. Love to see that video. So updrafts and downdrafts. From the side, or actually from a plane, this is what a downdraft looks like. Incredible to see that. The reason why it flares out like this is because as that air hits the ground, it's forced to spread horizontally. Beautiful to see that. All right, you want to turn any of these storms from being their ordinary, non-severe selves into some powerful, severe storms. Add our last ingredient, wind shear. You see, I told you that the storm dies because its downdraft cancels its updraft. What if we could separate the updraft? We can do that using wind shear. Wind shear is a change in wind speed and direction with height. Where do we find it? On our soundings. Now, way back in the 1990s, we were doing some of the very first simulations of storms on supercomputers. So in the 90s, this was as good as it got. But we wanted to simulate the effects of wind shear on a thunderstorm. So check out this animation here. In this environment, there is no wind shear. So each air represents the wind speed as you go from the ground up. They're all the same length, so the winds are not increasing with height. Watch what the storm does. It's the gray blob in the middle. It ascends and then descends. What went up came back down. The downdraft canceled the updraft. And after 2 hours, the storm is completely dead. Watch it again. Updraft goes up. Downdraft comes right back down it, shutting the whole thing down, killing the storm. Same simulation as we see here. I'm now going to add a wind that gets stronger with height. See how the arrows are getting longer? Watch this storm. Now the updraft is going up and it's being blown downstream. And as a consequence, the downdraft is not falling back through the updraft. And the storm lives. It strengthens. And instead of being killed after about an hour or two, this one reaches its severe limits. The distinguishing characteristic between non-severe storms and severe storms is wind shear. Watch it in real life. I know these are simulations. Here's the real thing. Now, no wind shear. Watch the storm. See, we got a little bit of music in the background for you. Storm, the updraft is going up. See it there? Unstable atmosphere. We're above the LFC. Cloud is being made. If we zoom in, we can see beautiful rising parcels of air full of energy, and they're ascending. They're making precipitation particles, and they're getting heavy, and they're trying to fall out of the storm. The problem is no wind shear separates them from the updraft. And as the music, which is kind of depressing, tells us, wow, the storm is collapsing in on itself, basically killing itself. Add a little bit of wind shear, and things become a whole lot more fun, and so does the music. Watch this. The winds are getting faster with height. Watch this storm. Got a little more techno here. Notice how the updraft, as it ascends, is being pushed off to the left. See it there? This means as the downdraft forms, it's going to form on this side, letting new cells build over here. You see, wind shear changed everything for this storm, allowing it to survive. Now, you remember when I taught you about hurricanes, hurricanes are killed by wind shear. That's not what happens with our severe storms. They feed off of it. At this point in this video, the storm was already collapsing. This one is healthy, it's mature, and it is about ready to become a severe thunderstorm. That's the role of wind shear. Now, check this out. This is a sounding for at least one of the soundings like I like to look at it in my nerd world here, okay? This gives me a wealth of information. I'm going to take you to Saturday, October 21st, 2017. There was a massive severe weather outbreak in Norman, Oklahoma. And here we are in northern Oklahoma. A sounding was launched around noon on that day. Now, it's a little complicated, but this line here is my temperature line. This is my dew point temperature line, and the parcel line is dashed. Now, what did we learn? Well, we know we want to be looking for the equilibrium level. We know we want to look for the LFC and the LCL. Well, where are they? Well, look for the kink. See it right there? That's the LCL. Right here, that's the LFC. And up here is the equilibrium level. This thing had a lot of CAPE in it too. There it is. How much? 2,265 joules per kilogram. What was the lifted index? -7. Did we have any wind shear? Absolutely. Look, surface wind 25 knots out of the south. Go up in the atmosphere, the winds are getting stronger and stronger, and they're even changing directions. Up here, the winds are 55 knots, so we're definitely bringing in some wind shear. Was it moist at the surface? Well, yeah. Dew point temperature was 64 degrees. Remember, we only want 60, so this is well above that. We had everything coming together, and in a snapshot, I was able to see all of it on this one diagram. Well, here's what it looked like in map form. Here's a map showing us kind of graphed out what CAPE looked like. We can see that the CAPE values where that sounding was launched, which was right here, are somewhere between 2,000 and 3,000 joules per kilogram. Plenty of CAPE. What was the lifted index? Well, the lifted index right in here was minus, in some locations, better than -8. Remember, we just need to be negative. We were very negative on this day right in through this area. What about our dew point temperatures? Well, look. Right here at this temperature level, we go above 60 in terms of our dew point temperatures. And look, we had plenty of moisture streaming up through the middle part of the country. Finally, did we have a lifting mechanism? Well, check it out. Here's our surface winds coming from the Gulf of Mexico, bringing in all the moisture, coming out of the Rocky Mountains in Canada, bringing in the dry air. It collided right there, and that was our front. All of that, all four ingredients came together right here in this area, and that produced these massive supercell thunderstorms that produced a lot of severe weather, a lot of huge hail, and a lot of problems for Oklahoma that evening. Incredible to see it all coming together. These are the four ingredients that we've been discussing, and now you can see it all happening in one time, producing severe weather. Well, I hope you found this informative. I hope you can really see the result of what we're talking about here. It's amazing to see how the atmosphere is able to bring these things together to produce incredible severe weather. Storm Chasing 101 begins with identifying those four ingredients: unstable atmosphere, trigger mechanism like a front, plenty of surface moisture, and wind shear. It happened all together in Oklahoma on Saturday. Incredible to see this all unfold.